So I think your screen is not quite full yet. It doesn't show the full size. So it was better before. Then you have to rotate your iPad.
Okay, welcome back everybody to this Symmetry seminar. A reminder to the participants, please feel free to unmute yourself and ask questions. We're very happy to encourage discussion, and without further ado, it's a pleasure to have Lorenzo Di Pietro to tell us about factorization and global symmetries in holography.
Thank you very much for inviting me to present my work. So yeah, today I will tell you about a work that I've done recently in collaboration with Francesco Benini and Christian Copetti from SISSA. And so let's start with some introduction. So the starting point is the celebrated holographic correspondence, which broadly speaking is a correspondence between a certain quantum field theory on d-dimensional background, let's say MD, and a dual quantum gravitational theory with which is defined to have the same MD asymptotics. So it's a d+1 dimensional quantum gravity theory with certain fixed asymptotics. Now, recently, people have found examples of this correspondence, which are solvable low-dimensional examples, but they have a different flavor, a different feature, which is that the quantum field theory on the boundary is actually replaced by an ensemble average of quantum field theories. Let me briefly mention some examples. So one example of this is in the two-dimensional dilaton gravity theory known as Jacquet-Teitelboim or JT gravity. And this theory is holographically, it captures holographically the low energy sector of the so-called SYK model, which is a quantum mechanical model of n Majorana fermions with certain with a certain quartic interaction with a random quartic coupling. And in the context of this JT gravity, people, these authors, were also able to compute the path integral with some fixed boundary and sum the result over all possible bulk geometries with this fixed boundary. And they were able to show that this is in fact the same as the answer you would get for a certain quantum mechanical model on the boundary, in which the Hamiltonian is drawn stochastically from a certain random matrix ensemble. Okay. And then there is another example that I want to mention, which is this time is in 3 dimensions, and this is given by Chern-Simons theory in 3 dimensions, supplemented by a certain prescription to sum over hyperbolic geometries, which here I call topological gravity. This was considered by this set of authors, and what they found is that by taking the answer for the abelian Chern-Simons theory, say U1 to the 2D, and summing the result over topologies, they get the same answer as what one can compute from the CFT of D compact bosons. The CFT has a large space of exactly marginal couplings, the so-called Narayan moduli space. And so what one has to do to match this answer summed over topologies is to take the answer from the compact free bosons and average it over this moduli space with a probability measure, which is just given by the so-called homological metric of the moduli space. Okay, So this was just a review, some examples that appeared in the literature. And the existence of these examples raises some questions. And so the first, let's say, obvious question is, when is it that a certain quantum gravity theory is dual to an ordinary quantum field theory, and when is it instead it is dual to this kind of ensemble averages? And just to make sure, like, I want to stress that this question makes sense in the sense that it is really not the same. Like, an average of quantum field theories is not the same as a single quantum field theory. And a smoking gun for this is the lack of factorization. So what does that mean? It means that for if we have an ordinary local quantum field theory and we consider it on a geometry which is made by many disconnected components, then a local quantum field theory is supposed to give a factorized answer, which is just the product of the partition function on each disconnected components, on each disconnected component. On the other hand, if instead we have an ensemble average of quantum field theories, what you're instructed to do is to first compute this partition function and then do the average over our random couplings. And in this case, we are not going to get the same as the product of the averages, but this is just, or at least in general, we're not going to get the product of the averages because this is exactly the variance of our probability distribution. And in these examples that I mentioned, this lack of factorization has a clear holographic interpretation because it's due to the presence of geometries in the dual bulk gravity theory that connect the two boundaries. Okay, so the presence of these contributions to the gravity theory is such that one doesn't get a factorized answer. So given that, so to refine a little bit the previous question, as I just said, in this example, we are getting something which is similar in a sense to a quantum field theory, but it doesn't have all the properties that we would like to ask to a, let's say, good quantum field theory. So a refinement to the previous question is, what is the property, the dual property on the gravity side that is somehow lacking in these gravitational theories, and that doesn't allow the dual to be a full quantum field theory. So this is what I mean by the second question. And for instance, one could imagine that in the kind of semi-classical approach that is using these examples, one is missing some important UV contribution, that just to make an example. And so this is also something that one would like to explore, and it's been explored in the literature. And related to this, the third question that I want to mention is, in these examples, can we somehow modify the gravitational theory, or perhaps complete it in some way, in such a way to change the dual from an ensemble average to a single quantum field theory? Okay, so these are the set of questions. And yeah, as Matthew said, please stop me at any point if you have questions. And so the goal of our work is to provide an answer to these questions in a very specific context, which is a toy model for the holographic correspondence. And this is the toy model provided by, on the gravity side, we are going to have Chern-Simons topology of quantum field theory with the compact gauge group. And more precisely, we're going to consider a gauge group of this form, which is a product of some group G with level K and the same G with level minus K for, say, some positive integer K. And the dual side, the dual quantum field theory side, will involve a rational conformal field theory. which will be based on this on the chiral algebra G level K. So it will have this symmetry both on the left and on the right. So that will be our goal. And I will just now give you a brief summary of the results and anticipate what we're going to say in the rest of the talk. So in this context, we are going to see that somehow what is responsible for Chern-Simons theory not being a good quantum gravity theory in the holographic duality is the fact that it enjoys a global symmetry. And so this resonates with the expectation, or some context even theorem, that good quantum gravitational theory should not have any global symmetry. And what we are going to do is to indeed show that in this case the modification that I mentioned before exists. So what we're going to do to modify the theory is to get rid of this symmetry by gauging it. And the upshot will be that gauging this symmetry will give us a modular-invariant CFT dual without the need to perform a sum over geometries, a sum over topologies. And so this will be connected to the fact that we will be able to see a factorized answer, because we will not need to include, or let's say that the result on a wormhole geometry will be automatically factorized. And a further outcome of this will be that we will see a way to turn the correspondence between Chern-Simons and the rational conformal field theory into a full holographic duality. Okay, so now this was just a short summary, and now I'll go and give you more details. Other questions at this point? Okay, so if not, let's start. So we'll start first describing how this works in the simplest case, which is the William case. So we will consider a Chern-Simons theory with the gauge group U1 at level K times another factor, which is U1 at level minus K. And we'll take K to be a positive even integer. So this is our action, simply the action for the Chern-Simons theory that I just said. So we have a gauge theory A, a gauge field A, and a gauge field A tilde. And let's start describing some salient features of this theory. So what are the dynamical objects? Let's say the dynamical objects are the lines of the theory. So the lines will be labeled by two charges, lambda and lambda tilde. And these charges, lambda and lambda tilde, will take values from 0 to k minus 1. Okay, these are the possible lines for this theory. And these numbers simply represent the U1 charge of the line, of the Wilson line. Now, these lines are topological operators, are topological lines, and as a result, they can be viewed as giving to the theory a global symmetry. Okay, let me just briefly explain this global symmetry. So the charged objects under this global symmetry are the line themselves. And the way one can measure the charge of a line is simply by considering this configuration in which two lines are grading each other. So one of the two we are going to see as the charge operator. Let's say this L1 that I call Q is going to be the charge operator, and the other line we can view as the charged object. And by well-known formula for grading of the abelian Chern-Simons, we're going to get just this space in front. which is fixed in terms of the charges. And so this tells us that the lines generate what is called a one-form zk times zk symmetry. Okay, the fact that it's a zk is just because the labels go from 0 to k-1, and you can see from this phase factor that the answer doesn't change if we shift charges by k. Okay, and also you can study how the lines fuse with each other and see that the charges simply adapt in the way that you would expect for a zk symmetry. Okay, and probably I don't need to explain this to the audience of the symmetry seminar, but this is called a one-form symmetry, and the idea is that it's the concept of one-form symmetry is also a generalization of the ordinary symmetry, in which instead of having a codimension 1 topological operator and charged objects which are local point-like operator, in this case we have codimension 2 operators, charge operators, and the charged objects are lines. Okay, so the upshot so far is just that in this theory we have a one-form symmetry, and I will use this one exponent to denote that it is a one-form symmetry, zk times zk.
A question?
Yes.
So, this phase also reflects a Tuft anomaly?
This phase also reflects a Tuft anomaly, yes, because it means that the charge of the symmetry is charged itself. So this means that like inside this full group zk times zk, most of it is has a Tuft anomaly, but we will see that there is a subgroup that is probably is already clear from the formula. There are some part of it which is free from Tuft anomaly. Okay, so then what are we going to do next? Since we want to use it for holography, we're going to take this theory and put it on a space with boundary. Here I just depicted a cylinder, so you can imagine a solid cylinder. And then on the boundary of this solid cylinder, we're going to put holomorphic boundary condition, let's say for the U1k factor, and anti-holomorphic boundary condition for the U1 minus k factor. And it is an old well-known result that by using these boundary conditions, one gets on the boundary U1 level k on the left and the U1 level k on the right, chiral algebra. Okay, and from this literature, we know that if, for instance, we take the partition function of this Chern-Simons theory on the solid torus, and we insert along the non-contractible cycle one line of charge, let's say lambda lambda tilde, what this computes for us are the extended the characters of this extended chiral algebra, which are again labeled by the charges, okay, and of course the level, okay. Okay, so in this case, since I am doubling the theory, so I have both the part with positive k and the part with negative level, I'm going to get the product of a character and the complex conjugate character. And a more general result is that if I compute on a more generic three-manifold with a boundary, and I can imagine various insertions of lines, or perhaps also lines that have endpoints on the boundary. This in general is going to compute for me some conformal block of this U1k left times U1k right chiral algebra. Okay. So far this was just a short review of some features of Chern-Simons. Now, suppose we want to take this Chern-Simons theory and we want to try to interpret it as a gravity side of a holographic duality. So there are some pros and some cons. So what are the positive aspects? Well, on one hand, this theory being topological is a general covariant, doesn't depend on the metric of space. So that's what we would like also for the gravity side of holographic duality. Another positive feature is that, as we just briefly reviewed, the partition function on spaces with boundary has a natural 2D CFT interpretation, so that it gives rise to some conformal blocks or some characters of that have an interpretation in terms of 2D CFT. On the other hand, there are some obstructions, some cons. The first one is that the answer that we are getting is not modular invariant. For instance, if we take just the solid torus without inserting any line, we're just going to get the characters of the trivial representation of the parallel algebra. And this by itself is not a modular invariant contribution. And the other negative feature that we also just reviewed is that it has a global symmetry, this one form global symmetry that is not expected to exist in a good quantum gravity theory. And I want to stress that these two cons are actually can be seen to be related to each other. So let me explain what I mean. So the fact that there is a global symmetry can be seen as causing the fact that our answer, if you compute the partition function with a certain fixed boundary, the answer is going to depend also on the three-dimensional topology. And just heuristically, this is due to the fact that, as I try to depict here, we can insert some of our non-trivial topological operators in the bulk, and these topological operators are going to be able to detect the topology of the three-manifold. And so we're going to get different answers depending on the 3D topology that has this fixed boundary. And on the other hand, this dependence on the topology can be seen as the cause of the lack of modular invariance of the answer. What do I mean by that? I mean that if there is this dependence on the three-dimensional topology, then the answer we're going to get, almost by definition, is not going to depend just on the geometry of the boundary, which can be seen as the requirement of modular invariance. For instance, if you have a, here I try to depict a solid torus, okay? So the square, if you do the identification, is going to become a torus. And if you compute the partition function of Chern-Simons on the solid torus, we get an answer which depends on which cycle of the boundary torus becomes contractible in the bulk solid torus. And this is what causes the fact that the answer is not going to be modular invariant, because I need to pick a cycle to be the one that shrinks. Okay, so we see that the existence of the global symmetry and the lack of modular invariance can be seen to be somehow related to each other. Okay, so now how can we proceed if we really insist on trying to interpret Chern-Simons as a quantum gravity theory? So one thing that we could try to do is to take our answer. Here there is. We can take our answer for the Chern-Simons partition function on a certain fixed boundary, and then to obtain modular invariance, we can just decide to sum over all possible topologies in the bulk. So this guarantees that we're going to get an answer which only depends on the boundary geometry, and so it's modular invariant. On the other hand, this also generically leads to an ensemble average on the boundary. The reason for that is that, for instance, if we consider again the disconnected boundary with two disconnected components, if we sum over all possible geometries, we're going to have a contribution from the disconnected geometry, but also contribution from the connected one, the wormhole, the Euclidean wormhole. And this is going to give rise to difference between the square of the average and the average of the square. This approach of summing over the bulk topologies is the one that is pursued in the non-rational case that I mentioned at the beginning as an example. These authors. And it has also been actually studied in the rational case by these authors. And our approach will be different. And what we will do instead is to get rid of the global symmetry. And we will get rid of it by gauging it. And like according to it might be not so surprising given the logic that I just explained, but what we are going to discover is that if we get rid of it by gauging, we'll also lose completely the dependence on the 3D topology. Okay, and we can see this as some strong form of general covariance, in which the quantum gravity theory, the answer that one gets is fully just fixed by the boundary asymptotics. And it is a bit reminiscent of what has been found recently also in a very different context, which is by this author, it was found in the context of the tensionless limit of ADS 362. And by this other author, it was a similar result of independence of the geometry was found in the context of so-called SYK with 1 point. Okay, so if there are no questions, I will now go ahead explaining this gauging of the one-form symmetry that we're going to perform. Okay, so suppose now we have this dk times dk one-form symmetry, and we want to gauge subgroup. So let me just briefly explain how we're going to do that. The gauging is going to amount to summing over bundles for this symmetry. So we might expect that is given by a certain sum over the H2, the second cohomology of our base manifold with values in our subgroup A, and in this case it's H2 because we are dealing with a one-form symmetry. So that's why let's say roughly speaking, the gauge fields are 2 points. Now, we are particularly interested in understanding how to do that in the case of a manifold with boundary because of our holographic application in mind. And it turns out that it is actually convenient in this case to, instead of viewing it as a sum over H2, to use Poincare duality to express it as a sum over the first homology H1 of our base manifold with still with coefficients in our subgroup A. So what's the way to understand this sum? This is now a sum over line insertions, right? We're going to take 1 cycles in our geometry, and there we are going to insert lines which correspond to the generators of our group A. Okay, and so there is a formula which one can write down for the partition function of the theory with the gauged one-form symmetry in terms of the partition function for the ungauged one with a background, well, sorry, this is not a background, this is insertion now of a line A. And the formula, what are the features? So we're going to have to sum over elements of the the first homology, which is what I just said, the sum of line insertions. And an important feature is that we need to include these prefactors, and these prefactors are fixed, requiring that this gauged partition function satisfies certain gluing conditions. Namely, what I mean is that if we have two manifolds with boundary, we would like to be able, if they have the same boundary, to sum over partition function with the same boundary condition on the two sides and recover the partition function for the gauge theory over the full manifold without boundary. And this is what can be used to fix these coefficients. And here I denoted the partition function for the one-form gauge theory to be labeled by some B. What is this B? B is basically the possible endpoints for the lines that I'm inserting. So in principle, I can also allow the lines that I'm inserting in the bulk to end on points which live on the boundary of my space. But for most of what follows, I will just not allow this. So I will just consider this B to be a trivial element of the H0.
So in general, this is actually not one cycles, but it's sort of relative one cycles, right? That you're summing over then. Because the notation is a bit confusing. The boundary of A is B, but then A is an H lower one. So.
Right, yes. I meant that in general here, I should have put, to be more precise,
Yeah.
A certain P, which is a choice of one point for each boundary component, for each connected component of the boundary. Yes, so by this B, I mean that I can choose such points, and I can in principle allow my bulk lines to end on these points. But I will mostly not do that, just fix what I would call Dirichlet boundary conditions, in which I just don't allow my lines to end on the boundary. Is it?
I have a question.
Yes.
In 3 dimensions, if I gauge a discrete one-form symmetry, don't I pick up a new zero-form symmetry?
Yes.
Do you get by putting extra phases in this formula?
Yes, I definitely do.
Does that change the argument, or? Yeah,
I have a backup slide if you want to see the details. But basically, what happens is that you're gonna get for the particular gauging that I'm gonna do, I'm gonna get a dual zero-form symmetry, and this symmetry, however, will not act on anything, so it will be trivial in this sense.
Will it act on what? Will it act on nothing at all, or will it just act on?
Well, basically,
will it only not act on genuine local operators?
My goal to achieve this topology independence is that I want to do this gauging in such a way to get trivial theory in the bulk. So I will not have any line operator anymore, and therefore this symmetry will be completely inert, will not do anything.
Thanks.
Okay. Oops. So what kind of subgroups of this zk times zk can we gauge? As Matthew was anticipating already before, we have to impose some anomaly-free conditions. So one condition that we require when we gauge a one-form symmetry is that the lines should carry integer topological spin. And this in turn implies that they're also mutually transparent. Okay, so this is also something that we want in order to be able to unambiguously gauge the one-form symmetry. And so now we can start asking what subgroups of our zk times zk satisfy this condition. So one subgroup that certainly does that is the diagonal zk subgroup. So the one generated by lines in which I put the same charge on the left factor and on the right factor. So this lambda tilde equal, lambda tilde equal lambda, okay? And this is clear from the formula that I showed before, like because there is a cancellation between, I mean, these objects are mutually transparent because of the k and minus k. But this is not the unique choice. There are other choices possible in general. And these other choices I will denote like this omega. So what is this omega? This omega can be thought of as a automorphism of our algebra of lines. And what we are going to require is that by multiplying the charge lambda by this parameter omega, we should get the same fusion roots and spin, okay, for the line with charge lambda tilde. Okay, and this, in order for this to be true, it's enough that this parameter omega satisfies this condition. And so we'll briefly mention then also this more general gauging. And an important property is that in both of these cases, I'm going to gauge a subgroup which has order k, and there is a counting that one can do on the number of lines that remain after gauging the subgroup. And this is given by k squared, which is the total number of lines that we have in the original theory, 1k times 1 minus k. And we need to divide this by the order of the group that we gauge also squared. And this, in this case, gives us just 1. So this means that upon doing this gauging, we land on the trivial theory. We don't have any line anymore. So this is the theory I want to consider. U1 level k times U1 level minus k divided by this gauged with the gauging of this one from symmetry. And this will be what I want to call my, in quotes, quantum gravity theory. And let me mention some properties that follow from the triviality, from the fact that the number, we don't have any non-trivial line after the gauging. So one property that follows is that the Hilbert space on any 2D geometry is going to be one-dimensional. So this means that we don't have so-called baby universes. The concept of baby universes has been related since similar paper by Coleman to the loss of coherence and the loss of coherence in quantum gravitational theories. And in this case, we see that we don't have any baby universe, which is good if we want to avoid getting these averages. And another property that the trivial theory, trivial topological theory has, is that we're going to get 1 for the partition function on any compact trimanifold. And this, in turns, can be, these two things together can be easily seen to entail independence on the topology. So suppose now we want to compute the partition function of our theory T on a certain with a certain fixed boundary. And let's say we have some complicated topology that depends on the boundary. Here, for simplicity, I'm imagining a sphere. Then what I can do is that I can always add 1 in the form of the partition function on a 3 sphere, because as I said, on any compact manifold, I'm going to get 1. And then I can cut the 2 three-dimensional geometries along, let's say, a 2 sphere. And then there is a property that follows from the fact that the Hilbert space on the 2 manifold is one-dimensional, and the property that follows is that I can basically always switch these two. When I insert a complete set of states, since there is only one state, I can always take this piece of the geometry and glue it to the other side, and vice versa. So when I do that, I get this much simpler geometry attached to the boundary, times, again, the partition function on a more complicated compact tree manifold, but this again is 1. So you see that now I get much simpler geometry in the bulk. So this means that after I do this gauging, thanks to the triviality of the theory in the bulk, all the dynamics is going to be due to the boundary, okay? And so let me explain what are we going to do if we want to compute some holographic observables in this theory. So again, our theory is the Chern-Simons gauged with this one from Symmetry gauged. So what we're going to do is that we're going to start with the computation in the Chern-Simons theory with holomorphic and anti-holomorphic boundary condition for the two factors. Okay, so this is what I depicted here, for instance, in the solid torus. I start to take my 3D geometry and I compute the result for the Chern-Simons theory. And then what I need to do is that I need to actually perform the gauging sum over the insertions of this object that I call A. This A is if you wish, is a composite line, which is the sum of all the elements of the group I'm gauging. And I need to sum this insertion of this A along the homology of my manifold. So for instance, in this case of the solid torus, I'm going to have to sum over the insertions of this element A in the non-contractible cycle. And then after I have this insertion, I will possibly simplify the answer I'm getting using some simple rules that follow from the property of this line, composite line A. So one property is the fact that since the lines are mutually transparent, I can just remove A in this way. And an important property that is going to play a role in the following is that if this A links a generic line of the Chern-Simons theory, projects it on a line belonging to A. So you see here what happens is that the label lambda tilde is forced to be equal to omega times lambda. And there is a factor in front, but that's not very important. And another property is that I can always, if I have an A object lying around, and there is also a line which belongs, which is also called lambda omega lambda, I can always fuse them in this fashion. Okay. So if you want now, this turns into a simple game of using these rules to simplify the answer. Okay, so now, oops, I explained what is the gravitational theory that I'm gonna use. Now let's see what is the corresponding conformal theory dual. So in this case, the dual two-dimensional theory is just a rational scalar. So it's just a simple free two-dimensional scalar field with compact, so it has a certain radius r, and it's going to be at the values of r for which this theory is a rational conformal field theory. So let's explain how this comes about. So let's take, for instance, omega equal 1. Okay, so I'm just gauging the diagonal zk. So now, as I said just in the last slide, the partition function of the theory T on the solid torus is going to be just the partition function of the Chern-Simons theory with this insertion of the object A in the non-contractible cycle. But now this object A can be rewritten as a sum over charges lambda going from 0 to so this should be k-1 of the partition function of Chern-Simons with this line inserted in the middle of the solid torus. And as I briefly with some slides ago, what this gives us is the product of these characters of the chiral algebra with the charge lambda. Okay, so what are we going to get as a result of this? We're going to get just the sum of products of all possible characters with the same charge on the left side and on the right side. Okay, but this is exactly what we would get for the partition function of a scalar field at the rational value of the radius r equal the square root of k. Okay, so these are the when the radius has this value, then usually we have an infinite sum over Virasoro primaries for the partition function of the compact boson, but in this particular value square root of k, we can reorganize it into a finite sum of this product of extended characters. And each term of this sum, we should view it as just the contribution of a certain primary of the U1k left, U1k right chiral algebra that is enjoyed by the scalar field of this value of the radius. Okay, so the primary will be the product of the left and right chiral vertex operators with the same charge lambda. Okay, is this example clear? Okay, so and we see that indeed we got a modular invariant answer because now we are summing over all the primaries. We don't have just one contribution. So this calculation of the solid torus suggests that this U1k, this theory T, that I call T, the gauging of the Chern-Simons with the homomorphic and antiromorphic boundary condition, corresponds, is holographically dual to a compact scalar with this value of the radius. And this was in the case of the diagonal gauging. And more generally, when K can be factorized, so take this form 2p times p prime, then we have more ways to glue the left and right characters of the chiral algebra, U1k to the left on the left and U1k on the right. There are more ways of gluing them in such a way to get a modular invariant answer, and these ways are labeled by a parameter omega, which can be written like so. Oh, the prime should have been on the P. In terms of two numbers R and S, which are fixed by this condition. Okay, and indeed this omega, this should be mod 2k. Sorry, there are some typos. And this omega satisfies that omega square is equal 1 mod 2k. And what do these different gluings labeled by k correspond to? They correspond to different rational scalars which have a different value of the radius. The radius in this case is going to be square root of 2p prime over p. Okay, so what we are seeing is that different choices of gauging in the bulk correspond to different prescriptions for gluing the left and right conformal blocks in such a way to get a modular invariant answer. Okay, of course, the literature on how to derive and understand the ways to glue the left and right answers to get physical conformal field theory is very rich. Here I just put some references, and here we are just seeing it in terms of this this gauging with the one from symmetry in the bulk. Okay. Here I just gave some examples of further checks that one can do of the match between the theory T and the scalar at rational radius. But maybe in view of time, I think I will skip them and go ahead. But if you want, I can show you later. So maybe one example that one check that I want to mention is a check of the factorization of the partition function on a geometry which is like a toroidal wormhole, Euclidean wormhole. So let's say we take the geometry which is T2 times an interval. So in this case, we have two boundaries, which are these two tori, okay, which I denoted as squared with some identifications. And now we have to follow our rules. So if we want to compute the partition function for the theory T on this geometry, what we are going to do is that we're going to insert the object A, this composite line, along the non-contractible cycles in the bulk. So these are just these two lines that I depicted here. And of course, it doesn't matter exactly in what order I put them. And this is the fact that we don't have Toft anomalies. And so now, how am I going to compute? So I want to show that this quantity factorizes. So we're going to get a separate contribution on the left boundary and the right boundary. And in order to proceed, I'm going to just cut my geometry and insert a complete set of states. Now, remember that here I'm doing a calculation in the Chern-Simons theory, because I'm just writing the answer in the T theory in terms of the answer in the Chern-Simons theory. So when I do this surgery here, I need to use the complete set of states in the ungauged Chern-Simons theory. And here, since the manifold is a T2, the set of states is given just by the lines of is labeled by the lines of the Chern-Simons theory. So when I cut open the geometry along this torus, what I'm going to get is a sum over the full set of left and right lines. And I'm going to have to insert this line on the two sides. Okay, here I'm being a bit careless about the normalization, but you can just trust me that normalizations work. I just want to show that indeed we get a factorized answer. And now, what am I going to do next to simplify my network is that I'm going to take this line over here and I'm going to just move it around one of the two lines. And I'm going to use my rule. So my rule told me that when I have the object A around the line, this projects it to the set of lines which have lambda tilde equal omega lambda. Okay. And so this basically eliminates for me the sum over lambda tilde. And the important point is that this also makes sure that on the other side, the two charges are going to be identified in this way. Okay. Now, finally, to go on, I can just, so I'm just left with one sum over lambda. And on the left side of the geometry, what I'm going to do is that I'm going to fuse this line with charges lambda omega lambda with my object A. And I'm going to be left just with the insertion of A on the left. Since I'm left just with the insertion of A, the sum over lambda moves just to the right part of the geometry. And when it moves to the right part of the geometry, you see that what it does for me is precisely it reproduces the definition of the composite object, the composite line A. And at the end, I found precisely the product of two partition functions on the solid torus for the theory T. Okay, so this proves the factorization. There is a similar calculation one can do for correlation functions. And also in that case, one uses that the line A projects to the physical operators. So in view of time, I'm going a bit fast on this. oops, there are other checks that one can do. For instance, one can consider the factorization of multi-boundary S2, the factorization with multiple boundary T2, and also consider the case of higher genus handle bodies. So let me summarize. We have seen that there is an holographic duality between this Chern-Simons theory with gauged one-form symmetry and a scalar with rational radius r squared, which is determined by the level k and the gauging, which I'm labeling with this omega, on the dual, on the boundary geometry. And what we saw is that the fact that we have no lines in the bulk ensures that all the dynamics is due to the holomorphic and antelomorphic boundary conditions on the boundary. And on one hand, this makes factorization obvious, but on the other hand, it's still non-trivial to check how this factorization is realized if we present the theory in this way as the gauging of the Chern-Simons theory. Okay, so I think my time is almost over. In principle, there are various generalizations that one can consider. And if you want, I can tell you some about the non-abelian case, but how much time do I have left?
We have 3 minutes, but we're of course happy to continue a bit afterwards and with questions and discussion. So,
yeah, well, I mean, I can just briefly, of course, the non-abelian case is a bit technical, but I can just give you some clue, some hint of how it works. So, yeah.
Maybe we could then pause to see if there are questions, and then
it sounds like
and then we can. I'm very happy to ask about the non-abelian case.
Yep.
Good. Well, thank you very much. Does anyone have any questions? So is there any so you mentioned if you have this situation where there's a lack of modularity, you don't have a modular invariant partition function. There was kind of two options. Either you can sum over topologies, or you can try to gauge the bad symmetry. And the sum over topologies is the one that leads to this ensemble averaging. Is it? Do you know if is that kind of always the case? Whenever you have this ensemble averaging, is there always this other option, or?
I mean, I think
how universal is the structure, I guess, is the question.
So I think there should be a similar story for the for JT gravity, for instance. Should be possible to, but the only problem is that it depends a lot whether you're considering. So in this case, we are doing a simple case in which we have a compact gauge group in the bulk. So it's somehow easy to identify this symmetry, this one-form symmetry, and we know the rules to gauge it, to somehow get rid of the dependence on the topology. And in the case of JT gravity, I expect this will be a little bit more difficult to be treated in the gravitational case. Sorry, I lost. I cannot see.
Okay. Okay. Any more questions?
Can I ask a quick question?
Yeah.
So if you change the boundary conditions from from Dirichlet to Neumann, then you're gauging part of the boundary Keren algebra, right?
Yes.
So is this removing part of the global one-form symmetry in the bulk? Or all of it, depending on what you gauge?
So you're asking if I change the boundary condition when I do the gauging, or
you change the boundary conditions to Neumann, say.
Yeah, but I didn't understand if you want to change the boundary condition for the Chern-Simons theory.
For the Chern-Simons theory, yeah, exactly.
Ah, I see. I think the point is that actually for the Chern-Simons theory, it's not clear to me that you have two possible boundary conditions. Let me explain, because like the theory is first order in derivatives, right? So typically what we do is just we have one choice, which is okay, you don't necessarily have to fix holomorphic. You could decide that you set some other component of the gauge field to 0, the boundary. But basically the only option you have is to fix some component of the gauge field to 0 at the boundary. It's not like, it's very different from when you have Maxwell, like when you have some.
That's true. Maxwell, yeah, I'm trying to remember if you have this option. Yeah.
Then you really have two possibilities. You have this Neumann and Dirichlet.
But there's some way to do the gauging on the boundary theory.
I think in Chern-Simons is basically bound to give you some kind of global symmetry on the boundary. But sorry, maybe that's not what you're asking. You're asking about if we can break the bulk symmetry using some boundary condition. That's your question, right?
Yeah, something that will allow this Wilson lines to basically end on the boundary and disconnect there or something.
Yeah, the Wilson lines actually are allowed to end on the boundary. And what they do is that they insert some chiral vertex operator, right?
Right, exactly.
And but then, yeah, I don't know if we can somehow, I mean, it seems a bit unlikely that by doing an operation just on the boundary, you can get rid of a bulk symmetry, like just by locality. Like if you have some symmetry in the bulk, I don't think you can really eliminate it by just doing some operation on the boundary.
Yeah.
Sorry. I think in our setup on the boundary, we don't have the one-form symmetry. It's broken by these holomorphic boundary conditions. So those give energy to the chiral vertex operators. Then you cannot really gauge the one-form, like the endpoints of the Wilson lines.
You're definitely right. Sorry, maybe I misunderstood the question. If the question was if we have the one-form symmetry on the boundary, then what Christian said is definitely true, and you don't have a one-form symmetry on the boundary. I had understood the question as whether the boundary condition can break the bulk one-form symmetry.
Yeah, that was the question. Yes. Okay. No, thanks.
You're welcome.
I also have a question.
Yes, please.
You mentioned that the dual symmetry, when you gauge, is not the problem because it doesn't act on anything.
Mm-hmm.
But that was, and that was a theory of pure gravity in some sense. If you were to add matter, would it act on something, the dual symmetry, or would still the arguments proceed and would the dual symmetry act on something?
Well, I have to say that at the moment, like there is even a preliminary question that I would have to answer for this, which is how to have a version of this theory with matter, and that I don't know how to do. But yeah, definitely would be interesting if there is something one can go along these lines. So
okay.
I cannot answer if I don't know how to do that first.
All right, thanks.
Okay, any more questions? All right, well, I'd be very happy to, if you have 5 minutes, I'd be happy to hear a bit about the non-abelian case.
Sure. Yeah, sorry for being a bit badly organized with time. So let me say a few words about the non-abelian case. So the generalization we want to consider now is the case in which we have GK times G minus K Chern-Simons theory, but now G is going to be a non-abelian gauge group. And again, the starting point will be to start just with the Chern-Simons theory with the holomorphic boundary conditions. And this is going to give us holomorphic, let's say, on the left and anthropomorphic on the right. And this is going to give us GK left and GK right chiral algebra on the boundary. And now we would like to find an analogous gauging that somehow, instead of giving us just this full chiral algebras on the left and on the right, gives us a modular invariant rational conformal field theory on the boundary. For instance, some WGW model. However, now the lines of the Chern-Simons theory do not form a group like in the previous case. So we need to do something a little bit more sophisticated. So one way to say this in modern parlance is that these lines now form what is called a non-invertible one-form symmetry. What does that mean? It means that instead of a group, the structure that is formed by the lines in this non-abelian case is that of a modular tensor category, and which means that what is a modular tensor category is just a category where the object are the lines, and we have morphisms are given by the junctions. Oops, and the crucial object that characterize this modular tensor category are the braiding and fusion matrices that tell us what happens when we, for instance, braid, or we try to do associativity on some configuration of lines. Here I'm being a bit schematic. There are many indices that these things actually carry. But okay. So what replaces the concept of gauging in this context? So this has been studied both in the TQFT literature and in the condensed matter literature. And the notion that replaces that of gauging a one-form symmetry is the concept called anion condensation. And so one needs to discuss the condensation of an anion, which is going to be some composite line. Again, I denoted here as A. And the important property that this object A, this line A, this composite line needs to have is that it needs to be what is called an algebra object. What does that mean? It means that we need to have a morphism from A, from the product of 2A, again 2A, okay? So that's why it's called an algebra object, because like we have a product inside. And this morphism needs to have some properties like associativity and commutativity. These two properties can be thought of as analog of anomaly-free condition that we had in the case of a group. Okay. Sorry, I realize this is a bit fast, but just to give you an idea. And now, how are we going to condense this anion? So what we have to do is consider a triangulation of the manifold. So we're going to divide it into tetrahedra. And then we are instructed to insert a network of this object A on the dual edges of this triangulation. And the nice thing is that thanks to associativity, it doesn't really matter how we construct this network of A inside the tetrahedron. And we're going to have some boundary conditions on the boundary manifold. So our tetrahedra will have some phases which lie on the boundary. And then on this boundary, we can either decide that our object A is going to simply end using this morphism from A to a trivial line, or we can decide that we are going to insert some operator on the boundary using some projector from A to the lines that compose A. And so the story now is similar. What we have to do is that we have to find one such gaugeable object A in such a way that the dimension of the category after the gauging is going to be 1, in such a way that we're going to have a trivial a trivial bulk theory. And this will ensure all the nice properties that we had before. And for instance, if we have gk times g minus k, one choice that always satisfies this is just to take this diagonal object, in which we take the same integral representation on the left and on the right, and we sum over all the integral representations. If we condense this object A, what we get is the diagonal WZW theory on the boundary, okay? And then there are, of course, other options, and understanding what are the options for this gaugeable object A, which give rise to a trivial theory, is the same as classifying all the possible modular invariants that one can construct out of some chiral algebra. For instance, for ST2 level K, there is an AD classification. And also here one can do various checks. One can consider the partition function on handle bodies, or one can compute correlation functions. And again, one finds the same answer in the condensed bulk theory and in the CFT dual. And another thing one can check is the factorization on the same geometry as before, the toroidal Euclidean wormhole. Okay, so maybe we should stop here, already took more time.
Okay, thanks, Lorenzo. Well, maybe at this stage, Lakshi, we could stop the recording and